Multiplication, not addition, from arithmetic through Newton's law of motion to a lifetime of learning. Number 1695, June 22, 2026. Gerald C. EclaireMD Foundation. Category, Self-Reflection. Arithmetic, Life Trajectory. Introduction. This article began with a simple observation from my TSI trajectory stress index model. During Father's Day, I dined out twice and consumed foods that I normally avoid, including higher carbohydrate restaurant dishes and pastries. My blood pressure remained relatively stable. Yet both my TSI 3B and TSI 3C values increased noticeably because my glucose increased. The mathematical explanation was straightforward. My TSI model is based on multiplication. TSI varies SPP times glucose. Blood pressure components remained stable while glucose increased. As a result, the overall TSI increased. This observation led me to a broader question: why do so? Many people naturally think in terms of addition while many real-world systems appear to operate through multiplication. I have observed a fundamental mathematical and philosophical distinction. Addition is linear and modular. It implies isolation, where parts can be added or removed without altering the nature of the other components. Multiplication is nonlinear and systemic. It represents interaction, amplification, and compounding. Newton's insight. One of the most famous equations in science is Isaac Newton's second law of motion. F equals m times a force is not equal to mass plus acceleration. Force emerges from the interaction between mass and acceleration. Although simple, this equation reflects an important principle. Nature often behaves through interactions rather than simple accumulation. Multiplication interaction. Addition is usually easier for the human mind. We naturally think in terms of separate pieces being added together. However, many physical systems do not work that way. The TSI example. Traditional clinical thinking often evaluates risk factors separately. Blood pressure contributes risk. Glucose contributes risk. Cholesterol contributes risk. Body weight contributes risk. This approach is practical and useful in many situations, however. My TSI model examines how variables interact when blood pressure remains constant and glucose rises. The TSI rises because the variables are multiplied together. Stable BP times higher glucose equals higher CITHIS is not merely a mathematical convenience. It reflects the biophysical reality that multiple physiological factors interact simultaneously within the same vascular system. The Father's Day example provided a clear demonstration. Blood pressure remained relatively unchanged, while glucose increased significantly. The TSI responded exactly as the multiplicative equation predicted. Athletics and performance. The same principle appears in athletics. Many people describe athletic performance as a collection of separate traits: speed plus strength plus endurance plus skill. However, elite performance often behaves more like performance varies as speed times strength times endurance times skill times mental focus. A weakness in one critical component can significantly reduce overall performance. An athlete may possess tremendous strength but poor endurance. Another may have exceptional endurance but insufficient skill. Success requires the interaction of many factors simultaneously. This is why elite athletes spend years refining every aspect of performance. They are not simply adding abilities, they are improving an integrated system. Music and artistic excellence. Musicians provide another example. A great symphony performance is not the sum of individual rehearsals. A performance reflects years or decades of accumulated practice, technique, interpretation, emotional maturity, discipline, and experience. Every concert contains traces of countless previous concerts. Every rehearsal influences future rehearsals. Every mistake becomes part of future improvement. The process is fundamentally multiplicative because each new experience modifies the performer, who then approaches the next experience with greater knowledge and skill. The musician is continuously transformed by prior learning. My high-technology career. When I reflect upon my own career in the high-technology industry, I see the same pattern. Many people only observe the visible success. They see a successful company, an IPO, or a business acquisition. However, those outcomes were not created by a few successful years. They were built upon 18 years of formal education, decades of engineering experience, multiple startup failures, thousands of long workdays, and continuous learning. I often worked approximately 100 hours per week for nearly 3 decades. The eventual success was not the addition of individual efforts. It was the product of accumulated knowledge interacting with accumulated experience over time. The entrepreneur I became at age 48 was fundamentally different from the student who entered college at age 16 because every stage of learning influenced all subsequent stages. My medical research journey, the same principle applies to my medical research. My work in medicine did not begin in medical school because I never attended medical school. Instead, my research emerged from the interaction of multiple disciplines accumulated over a lifetime. Mathematics contributed quantitative reasoning. Physics contributed system dynamics and cause and effect thinking. Engineering contributed modeling and problem-solving methods. Psychology contributed understanding of human behavior. Medicine contributed physiology, pathology, metabolism, neuroscience, and disease mechanisms. These different disciplines did not remain separate. They interacted continuously. Today, when I study glucose, blood pressure, stroke recovery, or neuroscience, I am simultaneously drawing upon knowledge acquired from many different fields over many different decades. The resulting work is therefore multiplicative rather than additive. The research purposes of this writing, I have completed approximately 1,695 papers with an average length of about 1,500 words. Simple arithmetic calculation suggests total exceeding to 0.5 million words, however. That number alone does not describe the true process. Each later paper contains knowledge acquired from earlier papers. Each paper incorporates previous discoveries, previous corrections, and previous insights. Paper No.1695 contains traces of papers No.1 through No.1694. Every new paper modifies the researcher, and the modified researcher writes the next paper. The process is therefore a feedback loop. Knowledge generates new knowledge. Learning generates new learning. The system compounds over time. A lesson from simplification: mathematics must preserve physics. While writing this article, I attempted to simplify the TSI equation further in order to make it resemble Newton's second law of motion F. And more closely, the original TSI model contains three variables. TSI varies SPP times glucose, where PP represents pulse pressure, SPP represents systolic blood pressure, and glucose represents metabolic stress. My reasoning was straightforward. Pulse pressure changes relatively slowly compared with glucose and systolic blood pressure, since PP often behaves like a slowly varying parameter. I explored alternative models that used only glucose and SPP. These simplified versions, represented by TSI for B and TSI for C, produced reasonable overall patterns and appeared mathematically attractive because they reduced the model to two dominant variables. However, when I compared the resulting trajectories with the actual stroke period, an important problem emerged. Without PP, the stroke period values became artificially low. The model lost part of its sensitivity to the underlying vascular condition, which functions as a damper within the system. This observation led me back to the original three-variable structure. Although PP changes more slowly, it carries important physical meaning. Pulse pressure reflects arterial stiffness, elasticity, and a long-term mechanical condition of the vascular system. In engineering language, PP behaves somewhat like a damping or stabilizing factor within the system. It may not dominate short-term fluctuations, but it provides essential information regarding the structural properties of the blood vessels. As a result, removing PP may simplify the mathematics, but it also removes meaningful biophysics. This experience reinforced an important lesson that extends far beyond this particular model. Mathematical simplicity is desirable, but simplification should never come at the expense of physical interpretation. An equation is not merely a collection of symbols. Each variable represents a real phenomenon. If a variable captures an important aspect of reality, eliminating it may improve mathematical elegance while simultaneously reducing explanatory power. Newton's equation, F equals m times a, works because mass and acceleration capture the essential physics of motion. The human vascular system is more complex than a moving object. In the case of TSI, glucose reflects metabolic stress, SPP reflects pressure loading, and PP reflects vascular stiffness and elasticity. All three contribute to the system's behavior. Therefore, the goal is not to make the equation look more like Newton's equation. The goal is to identify the simplest equation that still preserves the essential biophysical mechanisms. This analysis ultimately supports retaining PP within the TSI framework. The three-variable model may be slightly less elegant mathematically, but it better represents the physical reality of the vascular system. Conclusion: the TSI model began as an attempt to understand glucose, blood pressure, and stroke risk. However, it eventually led me to a broader observation. Many of the most important phenomena in life appear to be governed by multiplication rather than addition. Newton recognized this in physics through F equals m times a. Athletes demonstrate it through years of integrated training. Musicians demonstrate it through decades of practice and refinement. Entrepreneurs demonstrate it through accumulated experience and persistence. Researchers demonstrate it through continuous learning and knowledge compounding. When viewed through this lens, achievement is rarely the result of isolated efforts added together. Instead, achievement emerges from the interaction of knowledge, experience, discipline, persistence, and time. The longer the process continues, the more powerful the multiplication becomes. Epilogue. Returning to arithmetic while writing this article, I found myself reflecting on a subject that most people encounter during elementary school but rarely revisit in later life: arithmetic. For most of us, arithmetic consists of simple operations such as addition, subtraction, multiplication, and division. We learn how to use them, but seldom stop to ask what they truly represent. This article began with a practical observation involving my TSI stroke model. On Father's Day, June 21, 2026, I consumed more carbohydrates than usual while dining out twice. My blood pressure remained relatively stable, but my glucose increased, causing both my TSI 3B and TSI 3C values to rise. The mathematical explanation was straightforward. Because the TSI model is based on multiplication rather than addition. That observation led me to a broader question. What does addition represent? What does multiplication represent? Why do so many real-world phenomena appear to behave through multiplication rather than addition? Several months ago, Professor Jones commented that he found it interesting that I thought so deeply about arithmetic operations themselves. Most mathematicians, engineers, physicians, and scientists use arithmetic every day without questioning the meaning behind the operations. They use arithmetic as a tool. I found myself asking what each operation represents in physical reality. During this reflection, I also thought about the mathematician Archimedes. I have read many stories about his remarkable life and extraordinary devotion to mathematics, but I have not studied his original number theory papers in detail. Nevertheless, it seems difficult to imagine that anyone could spend a lifetime working in number theory without developing an appreciation for the fundamental role of arithmetic. Number theory is built upon integers, primes, divisibility, factorization, and numerical relationships. At its foundation lie the elementary operations of arithmetic. Yet even among mathematicians, most attention is directed toward the resulting structures rather than the philosophical meaning of the operation themselves. My own path was different. I spent decades studying applied mathematics, physics, various engineering, business administration, psychology, biomedicine, neuroscience, and pathophysiology. Ironically, after all of that complexity, I found myself returning to a very simple question: which arithmetic operation best represents reality? The answer that repeatedly emerged was multiplication. Newton's second law states, F equals m times a force is not mass plus acceleration. Force emerges from the interaction between mass and acceleration. Similarly, my TSI model can be viewed as an interaction among physiological variables. As I reflected further, I realized that one of the variables, pulse pressure PP, changes relatively slowly over time and often behaves almost like a constant. This observation makes the model resemble Newton's formulation even more closely. The dominant dynamic interaction often becomes the coupling between blood pressure and glucose. However, after examining the results from the two input models, I realized that the omitted variable remains physically important, although pulse pressure changes more slowly. It carries essential information regarding vascular stiffness, elasticity, and the damping characteristics of the vascular system. The same principle seems to appear throughout life. Athletic excellence is not merely the addition of strength, speed, endurance, and skill. These factors interact and reinforce one another. Musical performance is not simply the sum of individual practice sessions. Every performance contains years of accumulated technique, interpretation, discipline, and experience. Entrepreneurial success is not the addition of isolated business decisions. It is the product of knowledge, experience, persistence, timing, and opportunity interacting over decades. My own medical research journey over last 26 years follows the same pattern. Each paper contains lessons learned from previous papers. Each new discovery influences future discoveries. The researcher is continuously transformed by prior learning. Therefore, paper No. 1695 is not simply paper No. 1690 for plus another 1,500 words. It contains the accumulated knowledge and experience of all previous 17 years of hard work. Perhaps the most surprising realization is that, after nearly 80 years of life, I find myself returning to concepts first encountered in childhood arithmetic at the age of 6. Addition accumulates. Multiplication compounds. Addition builds collections. Multiplication builds. TRHACTORIS. Knowledge often begins with complexity, but understanding frequently returns to simplicity. In the end, this article may not be about glucose, blood pressure, diabetes, heart attacks, kidney failure, stroke, mathematics, or even medicine. It may simply be about a lifelong attempt to understand how learning, achievement, and human development actually occur. My conclusion, at least for now, is that many of the most important outcomes in life are governed not by addition, but by multiplication. Addition builds collections. Multiplication builds trajectories. This content is provided for education or reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.